We are now going to discuss categorical variables. They are very useful as they indicate if our unit of interest is a member of a category. For instance, if we are looking at cars, it could tell us if the car is red or blue, which are different categories of colors. Categorical variables are known by many names: dummy variables, indicator variables, or if you are doing machine learning, one-hot variables. They can take only two possible values, 0 and 1. So you will never see a categorical variable being equal to 0.5. When it's equal to 0, it means that the unit you are looking at is not a member of the category. And when it's equal to 1, it means it's a member of the current category. For instance, here I've put a dataset of phones, so you have different models: the Google Pixel, the iPhone, the Samsung Galaxy, and the Xiaomi Redmi. And then you have the category Android, and it tells us that the Google Pixel is a member of the Android category, whereas the Apple iPhone is not a member of the category, for instance. We can add categorical variables directly in our regression model. They will have their own coefficient. We always want to have a reference group though, otherwise interpretation and even estimation is going to be difficult. The reference group acts as a baseline and the coefficient for the other categories are interpreted relative to that group. For instance, if we're looking at two possible categories, either the phone is an Android phone, category 1, or it's not an Android phone, category 2. In that case, in our model, we could decide that the non-Android phone is the reference group, and then we would have in our equation a coefficient for the Android group. So non-Android phones are the reference group, we remove it from the equation, and we only keep the Android group. By doing so, we are going to first be able to get estimates for our coefficients, a bit more on that later, but also we have a nice interpretation. Here we are looking at a shop that sells cell phones, and we want to know the average number of sales each day, and for that we are going to use the Android category as an explanatory variable. Our estimates are 4.3 for the intercept and minus 2.2 for the Android category coefficient. In that case, the intercept is the average number of daily sales for the reference group, for the baseline, so for our non-Android models. Then the coefficient minus 2.2 for Android is relative to that baseline. So 4.3 minus 2.2, that is 2.1, is the average number of daily sales for Android models. We could reverse that equation and get instead the Android group as a reference group and put in the equation the non-Android indicator variable. In that case, we get these coefficients, 2.1 and 2.2. So now 2.1 is the average number of daily sales for Android models, which are the baseline, and 2.1 plus 2.2, which is 4.3, is the average number of daily sales for non-Android models. We can see that we have the same numbers in both cases, 4.3 for non-Android models and 2.1 for Android models. Why do we need a reference group? Well, without a reference group, there are infinitely many solutions to the regression equation. In that case, we don't know which solution to pick, so we don't know how to solve our minimization problem. And that's why we always need a reference group to act as the baseline. At the bottom here, I've put different fitted models. So they are the same model, but with different coefficients. And we can see that they all have the same predictions. So in the first equation, we have 2.1 as the intercept, 2.2 as the coefficient for non-Android phones, and I added 0 as the coefficient for the Android category. So that's equivalent to what we had as estimates on the previous slides. In that case, if the phone is a non-Android phone, the number of sales on average each day would be 2.1 plus 2.2, which is 4.3. And for the case of the Android category, we just have the intercept, 2.1 plus 0 times Android, and we get 2.1. In the second line, we have 0 as an intercept, 4.3 as a coefficient for non-Android, and 2.1 as a coefficient for Android. In that case, for non-Android group, we get 4.3 times 1 plus 2.1 times 0, because the phone is not a member of the Android group, which is 4.3. Same way for Android group. In that case, we get 0 for non-Android and 1 for Android, so that's 4.3 times 0 plus 2.1 times 1. It's 2.1. And you can play with a coefficient like that and find many solutions, infinitely many solutions, that will always give the same averages for the non-Android group and for the Android group. So remember, always pick a reference group. That group will have the intercept as an estimate, that's a baseline, and then all the other groups will have their coefficients relatively to the base group. What happens if we have many categories? In that case, each category becomes a separate variable. For instance, in a basketball team, each basketball player has a position and they could be grouped into 4 categories. We could have forward position, center position, guard position, or a guard-forward mix of positions. Here you have some data. For instance, Jordan Smith is a guard. So all the indicator variables, all the categorical variables will be 0 except for guard, which would be 1. For Trevor Bonhoff, it will be 1 for forward because this player is a forward, and 0 for center, guard, and guard forward. So for each of these players, we'll have 1 for the corresponding category and 0 everywhere else. Here you can see the output of a regression where I have the number of points per game for each player as a dependent variable and the position of the player as an exploratory variable. Now, there are 4 types of position. I have to pick a baseline, and I pick guard as the baseline. So there are only 3 explanatory variables left: the position of center, the position of forward, and the hybrid position of being guard or forward. Now, the intercept is the average number of points per game for our baseline, so for guard. So we can see that the guard position on average scores 5.3 points per game. Now, relative to that, if you are a center, apparently on average you score 1.3 points less than the average of a guard. If you are a forward, you score 1.15 points more on average than a guard. And if you are a hybrid guard and forward, then you score 5.98, so almost 6 points per game on average more than a guard in the dataset.